In lesson 13.2, we're going to look at algebraic limits and tangent lines. So we're going to graph the function f of x equals x squared minus 4x plus 3 over x minus 1. So we can factor x squared minus 4x plus 3 into x minus 1 times x minus 3. And that means that f of x could be expressed in simplest form as x minus 3 for x values that are not equal to 1. So in order to graph this, we can graph a line with a y-intercept of negative 3 and a slope of 1, but we're going to eliminate the point where x is equal to 1 and replace it with a removable discontinuity, which is a hole in the graph. From the graph now, we can look at limits. The limit as x approaches 1 of f of x is equal to negative 2, because as we come in from either side of x equals 1, the y values approach negative 2. F of 1, however, is undefined. Similarly, we can look at the limit as x approaches 4 of f of x, which is equal to 1. As we come in from either side of x equals 4, the y values approach 1. F of 4 is also 1 because there is no removable discontinuity at that point. Let's take a look at b. G of x is equal to x minus 3. So g of x is equal to x minus 3 is a line with a y-intercept of negative 3 and a slope of 1. There are no removable discontinuities. For this graph, which is almost exactly like the previous graph, the limit as x approaches 1 of g of x is equal to negative 2. G of 1 is also equal to negative 2. And as we approach x equals 3, the limit as x approaches g of x, the limit as x approaches 3 of g of x is equal to 0. And g of 3 is also 0. You'll notice that limits and function values agree for this function because we don't have any discontinuities. And that brings us to an important observation. If a function f is continuous at x equals a value, then the limit as x approaches that value and the value of the function at that point are the same. If a function has a removable discontinuity at a value, then and that function f of x can be simplified to a function g of x for x not equal to that value, then the limit of the function f as x approaches c and the limit as the function g approaches c are the same, and those values are the function value of g. That's a lot of words. Let's see what that means in practice. So in example 2, we're going to find each limit, and as x approaches 3, this function is nice and continuous. There are no discontinuities at x equals 3, so for my limit, I'm just going to replace x with 3 and find the function value. For any continuous function at a point, that the limit can just be found by finding the function value. So 3 squared is 9 plus 3 is 12 divided by 2, and our limit is equal to 6. Things get more interesting if we have a function with a discontinuity at the particular value of x that the limit is expressing. So we are approaching x equals negative 4, and at x equals negative 4, we are going to have a discontinuity. So what we're going to see if we can do is re-express this limit as the limit of an equivalent function everywhere except for x equals negative 4. As you're working your limit, bring the limit notation down, and then factor the numerator, x plus 4 times x minus 3. And now we're going to write a function that we're taking the limit of that's equivalent to the original function everywhere except for at x equals negative 4, and that function will be x minus 3. X minus 3 is a nice continuous function, so the limit as x approaches negative 4 of x minus 3 is just the same as the function value, which is negative 4 minus 3, which is equal to -7. What we're basically doing is finding the y value of the removable discontinuity, which is what we did in chapter 12. In C, we have a function that has a discontinuity at x equals 6, which is the value that the limit is approaching. And so I'm going to try to eliminate that discontinuity by writing an equivalent function everywhere except for x equals 6. So in order to do that, I'm going to simplify this complex fraction by multiplying by the LCD of the two mini fractions on the top, and then distribute that multiplication. And as you do that, remember to bring down the limit as x approaches 6. So when we distribute 7 times x minus x plus 1 to the first term, we get a result of 7 in the numerator. When we distribute to the second term, we get minus the quantity x plus 1. Downstairs, we just have a bunch of factors, 7 times x minus 6 times x plus 1, and I'm going to leave them in factored form. Numerator is not in factored form yet. We need to simplify the numerator by distributing the negative and then combining like terms. And when we do so, we're going to get 6 minus x. So now we can do some simplification. 6 minus x and x minus 6 are opposite factors, so when we cancel, we're going to get a -1. And now what we have is a function that is equivalent to the original function everywhere but x equals 6. And so its limit is just the function value, which is -1 divided by 7 times 6 plus 1, or -1/49. Once we substitute in the values of x at the that the limit is approaching, then we can drop that limit notation. In D, we have a function that we're taking the limit of that is discontinuous at x equals 4, so we're going to try to remove that discontinuity, and we're going to use our conjugate technique here. So I'm going to multiply by the conjugate, which is the square root plus 3. And if we multiply the numerator of the fraction times that expression, we need to multiply the denominator. And in our numerator, when we multiply, we get a minus, or rather a squared, which is the square of the square root, minus b squared, which is 9. And then divided by our factors in the denominator, and I'm going to leave those in factored form rather than multiply through, because our goal is going to be to get that x minus 4 to cancel. So continuing, the limit as x approaches 4 of x squared minus 16 divided by x minus 4 times the square root of x squared. That was a -7, I believe. Let me double check that. Yes, I've miscopied that. That was a -7. All right, and now we can factor x squared minus 16 into x plus 4 times x minus 4. And now we can cancel some common factors. Once we have done that, we've created an equivalent function that has no discontinuity at x equals 4. And so what we can do now is take the limit by finding the function value of the new function that doesn't have that discontinuity. So that limit would be 4 plus 4 divided by the square root of 4 squared minus 7 plus 3. And that will give us 8 divided by, and 4 squared minus 7 is 9, so the square root of 9 is 3. 3 plus 3 is 6, so 8/6, our limit is equal to 4/3. Okay, it's your turn to try. Try E on your own. Since this function had no discontinuity at x equals -1, we can just find the function value, and the function value is equal to the limit. Now pause the video while you try F on your own. For f, we can cancel factors of x plus 2 and now have a function without a discontinuity at x equals -2, and then just find its function value. Now pause the video while you try g on your own. For g, we can multiply by the least common denominator 5x over itself, and then cancel common factors and replace x with 5. Now pause the video while you try h. And for this question, we can eliminate the discontinuity by multiplying by the conjugate of the numerator over itself, remove the factors of x minus 7, and then just find the function value for the function that is equivalent everywhere but x equals 7. An emphasis of the beginnings of calculus is finding the slope of a tangent line to a graph. And the slope of a tangent line to a graph is the slope of the function at that point. So, we're going to find slopes of tangent lines by using this idea to find slope. Slope is y2 minus y1 divided by x2 minus x1, and f of x minus f of c over x minus c fits that bill. However, we want to find the slope at one point. If we try to find the slope at one point, we're going to have 0 over 0 as our slope, which is undefined. So the concept of a limit will help us to find that slope. So the limit as x approaches c is the limit as the 2 points mentioned here, for which x is equal to x at one point and x equal to c at another, approach each other, and the 2 points become 1. So in example 3, we're going to use the slope of the line. We're going to find the slope of the line tangent to the graph at each function at the specified point, and then use it to write an equation for the tangent line, and then we're going to graph it. So if we want to find the slope at x equals 1, then that slope will be equal to the limit as x approaches 1 of f of x minus f of 1 divided by x minus 1. F of x is x squared minus 5x. If we calculate f of 1, that is -4. So if we subtract -4, that's equivalent to adding 4. If we factor the numerator, x minus 4 times x minus 1, and cancel common factors, as x approaches 1, our limit is 1 minus 4, which is equal to -3. So that means at x equals 1 on our graph, the slope is -3. I'm going to draw a picture of that. Here's the point where x equals 1 on the graph, and then if I create a slope of -3 from there, we can see that the line that's formed is tangent to that graph. The point on the function is the point 1, -4, and the slope of that tangent line is -3, so the equation of the tangent line is y plus 4 equals -3 times x minus 1 in point slope form. Remember, point slope form is y minus y1 equals m times x minus x1. In B, we have the graph of a hyperbola g of x is equal to 6 divided by x at x equals 2 that we are interested in. And so the slope of our tangent line is equal to the limit as x approaches 2 of g of x minus g of 2 divided by x minus 2. And g of x is equal to 6 divided by x. G of 2 is 6 divided by 2, which is 3, and that's divided by x minus 2. We can use R, simplify a complex fraction by multiplying both numerator and denominator by the denominator x, and that gives us the limit as x approaches 2 of 6 minus 3x divided by x times x minus 2. Continuing, that's equal to the limit as x approaches 2 of -3 times x minus 2 divided by x times x minus 2. If we cancel our common factors of x minus 2, then the limit is of -3 divided by x. And Since that has no discontinuity, we can find our slope of negative 3 over 2. If we graph from the point on the function at x equals 2, we can see that the slope is negative 3 over 2, which is down 3 over 2, or up 3 and left 2, and graph that tangent line. And since the point in question is the point 2, 3, and our slope is negative 3 halves, written in point slope form, the equation of the line is y minus 3 is equal to negative 3 halves times x minus 2. In our last example, h of x is a square root function, and so the slope at x equals negative 1 is equal to the limit as x approaches negative 1 of h of x minus h of negative 1 divided by x minus negative 1, which is equivalent to x plus 1. H of x is the square root of x plus 5, and h of 1 is the square root of negative 1 plus 5, which is the square root of 4, or 2. We can eliminate the discontinuity in this slope function by multiplying by the conjugate of the numerator in both the numerator and denominator of this fraction, and that will give us x plus 5 minus 4 divided by x plus 1 times the square root of x plus 2 plus 2. And I've miscopied a 2 as a 5, I believe. And what we'll notice is that our numerator, x plus 5 minus 4, is the same as x plus 1, so we can cancel common factors, and now replace x with negative 1, and that will give us 1 over the square root of negative 1 plus 5 plus 2, which is 1 over 2 plus 2, or 1/4. If we go to the graph at x equals negative 1, our y value is 2, and the slope we just found from our limit is 1/4, so that means we can go over 4 and up 1 from that point of tangency, or over 4 to the left and down 1. And there's our tangent line, and our tangent line has a slope of 1/4, so the equation when written in point slope form is y minus 2 is equal to 1/4 times x plus 1.